Now that we've learned about CSMA-CD, I'm going to tell you about Ethernet. Ethernet started in the early 1970s. Originally it ran at 10 megabits per second, but has evolved a long way since then. In the first place, CSMA-CD was right at the heart of how Ethernet worked and determined how many hosts would share a single cable. We'll see later that it became less important as the speed went up. The original Ethernet looked like this. These are two pictures that were drawn by Bob Metcalfe, one of the co-inventors of Ethernet back in the early 70s. He was working at Xerox PARC at the time. He later went on to found 3Com. So on the left is showing the original topology that they had in mind of both wired and wireless Ethernet. And on the right shows the specifics of how the first Ethernet network was built. There was this big, thick yellow cable. It was always yellow. It was very, very thick and inflexible and snaked around in the ceiling or in the walls or under the floor. And then these big taps would be screwed down into the cable to make an electrical contact for an interface and then a computer. It became much simpler over time, ending up with what we use today. This is the Ethernet frame format. This is the format of the frames that are put onto the link. The first bit is shown on the left-hand side, and it starts with a preamble. The preamble is a sequence of ones and zeros just there to train the clock recovery circuits to help them get started and to have recovered the clock before the data actually starts to arrive. There's a starter frame delimiter, which is a special symbol which tells us that the packet is just about to start, we then go into the destination address, which we already know to be a 48-bit address. This is a globally unique address assigned by the manufacturer of the interface. 1 bit tells us whether it's unicast or multicast, and 1 bit can be used, in fact, to make it a locally defined address, although that's actually very unusual. So there's 46 bits that are there to define the globally unique address, and so there's a very, very large number of Ethernet addresses to use. The source address is just the address of the local host that's sending the frame in the usual sense. The type indicates what we'll find inside the data. For example, the ether type of hex 0800 is telling us that there's IP inside here, which of course is a very common case. You'll recall that there is a minimum size for any CSMA-CD based network, a minimum packet size. So we pad the packet if the data is very short. We pad it to make sure that there are a sufficient number of bytes so that we can detect collisions reliably before we've finished sending the packet. So they're padded out to a minimum of 46 data bytes. So if the amount of data is over 46, then of course it won't pad it. But otherwise it will pad it just to make sure that there's enough. And finally, there's what's called a cyclic redundancy check, CRC, or the frame check sequence. The CRC is checking the sequence using a code like we saw in the error detection videos that will tell us that whether or not there was an error in the bits. For example, if the bits were corrupted on the wire or in the end host before it was processed. The original 10 megabits per second Ethernet was standardized by IEEE and goes by the standard of IEEE 802.3. You'll often hear Ethernet being referred to as a .3 network for this reason, just as an abbreviation of 802.3. And this was just the standards body name that was used to write the spec that defined the correct operation of Ethernet. So it has really two components. It has the MAC protocol and the frame structure that we've just seen. And then underneath you had different options for the physical layer that could be used. There was originally what's called the 10-base-5, which was that big thick yellow cable that I described earlier. And that went out of fashion quite a long time ago. Then that was replaced by a thin coaxial cable version that used the coaxial cable similar to the RF cables we use for TV. But what really, really transformed Ethernet was when it started to use this type of cable here. This is the RJ45 cable that we're all very familiar with. And that was not because of the connector, it was because of the type of cable that it can use and also the topology of the network, and we'll see that in a moment. But basically it started to run over voice grade unshielded twisted pair that was already present in the walls of many buildings. It's called category 3 telephone cable. It's fairly low grade cable that was used for connecting telephones to the exchange at a company. There's also an optical fiber version called 10-base-F. It was originally used mostly by the military because they're harder to tap. There were 2 optical fibers and a single cable, one for each direction. Ethernet really took off when the 10-base-T standard came along for running Ethernet over twisted pair. So 10 megabits per second was carried over the category 3 twisted pair telephone wires that already existed in pretty much every building in the world. They were arranged in a star. In other words, that those twisted pair cables would go to a wiring closet on their way to the telephone exchange. So not only did the twisted pair cable really help Ethernet be successful, but this topology of having an end host connected by twisted pair into a hub, and a hub was a repeater. It would take every signal coming in and then repeat it over every outgoing cable except for the one through which it entered. So it didn't actually understand the packets, it would merely repeat them electrically. If there was a collision, then the collision would take place anywhere within here. It would be detected, and the hub would make sure that the voltage levels were sufficient to make sure that it could be detected. Also, this centralized management in this hub, this would be managed by the network administrator, and this central management, rather than the distributed management of crawling under the floorboards or up in the attic, made it much easier to manage Ethernet once these hubs were placed in these central locations. So this led to a huge growth in Ethernet in the mid-1980s. Over the years, people wanted to make Ethernet faster and faster, so 10 megabits per second gradually was increased to 100 megabits per second, and then gigabit per second, and more recently 10 gigabits per second, so 1,000 times faster than the original Ethernet spec. One problem that we have to solve when increasing the size of Ethernet is if we're using CSMA-CD, then we need to make sure that that we keep this requirement that P over R is greater than or equal to 2L over C. In other words, the duration of a packet is longer than the round trip time, so that we can make sure that we're still transmitting a packet when a collision is detected. So when we increase the speed of the network, when we increase R, in order for this to be true, we either need to make P larger to counterbalance that increase in R, or we need to make L smaller. And so this was a design choice when Ethernet was made faster. And the solution was to keep the packet size the same. Because if we'd made the packet size 10 times larger, from 64 bytes, which was the original, up to 640 bytes, then many of the packets that we'd like to send would be smaller than that, things like acknowledgements and DNS queries, things like that. And so it would be very inefficient. So the decision was to keep P the same, but to make L smaller. So 100 megabit per second Ethernet and gigabit per second Ethernet both have this requirement that L is limited to 100 meters. This turned out to be much easier with the introduction of Ethernet switching, as I'll describe in a few minutes. So as we made it faster and faster, the Ethernet MAC protocol stayed the same. That's the framing structure and the way in which we decide when to send packets onto the wire. That stayed the same for a while. And the 100 megabit per second Ethernet was called fast Ethernet. Doesn't seem so fast these days. And there were 2 standards for the physical layer: 100 base TX, which was the coding structure used for twisted pair cable, and then 100 base FX for optical fiber. On the 100 base TX, it uses category 5 cable again, and the same RJ45 connector that we've seen. It actually started to be full duplex, meaning there were 2 pairs that were used rather than just one within the cable. One pair was used for 100 megabits per second signaling in each direction. Instead of using the Manchester encoding, it started to use 4B, 5B encoding, which we saw as the means to introduce transitions for clock recovery. We saw that in the video about clocks. And of course, it was limited to a distance of 100 meters. Then later came along the 1 gigabit Ethernet standard. There was the 1000 base T and the 1000 base FX. That should be 1000 base T. The 1000 base T standard also runs over category 5 cable using the RJ45 connector. As many of the laptops and servers that are sold today, the Ethernet in them is 1 gigabit per second or 1000 base T. It turns out it's very hard to carry a 1 gigabit per second signal over a category 5 cable. So they actually use 4 pairs inside the cable, and they carry signals in both directions at the same time over all 4 pairs. So there's no room for anything else on this cable. It can only be used for the gigabit Ethernet. It uses a very complex coding, which is beyond the level of what we're going to be describing in this class. And it used 5-level signaling. So instead of just using a binary on-off, as was used in the original 10 megabits per second Ethernet, it uses 5 different levels to try and pack as much signal, as much information onto the cable as it can. And as before, the distance is limited to 100 meters. By the late 1980s, 10BASE-T Ethernet was extremely popular. There was already work going on 100 megabit per second Ethernet, and it was clear that the networks would get faster and faster. The hubs and the repeaters in the wiring closets meant that the networks could be really quite large and were being deployed on a very large scale. But it was clear also that for faster and faster networks, each of the segments was going to get very, very short, just down to 100 meters. So with a large number of hosts sharing a small network, the networks tended to be overwhelmed with the number of collisions that they would see, because there were just so many hosts all trying to talk on the same network. And so it became natural to try and partition those Ethernet networks to reduce the number of collisions, what's often referred to as reducing the collision domain. At the same time, cost of switching hardware was coming down. It became easier to build ASICs, or specialized chips, for doing the switching. And so all of these things together led to partitioning networks using Ethernet switches. So with a hub or a repeater, every time a packet is sent, the whole medium of all of these 5 links would become busy and would be used up. So within this circle here, the entire capacity is, say, 10 megabits per second or 100 megabits per second, depending on the rate. So with large networks with, say, hundreds of end hosts all connected to a hub or a set of hubs, this would be very limiting in the total overall capacity that they had to use. What if we could allow several communications to take place at the same time? So for example, if A wants to talk to B at the same time that C is talking to D, because they're talking to different hosts, different sets of hosts, why don't we allow this by allowing the communications to take place independently? So instead of the hub repeating the signal just as an electrical signal, what if it was to actually interpret the packets, send the packets only to the correct destination, just like a router does, but based on the Ethernet addresses rather than the IP addresses? So this is what was called a switch. Before being called Ethernet switches, they were called bridges. You will see those referred to sometimes, but we're just going to call them Ethernet switches. So the basic operation is, if A is sending to B, the packet will flow down to the switch. The switch will look at the Ethernet address, decide where to send it next. If it has it in its table, then it will forward it to B. And at the same time, perhaps C is sending a packet to D, and the same thing will be happening over here independently. So the collisions now are just held within a single cable. So if there happen to be signals going in both directions on the cable at the same time, that might cause a collision. Although at the same time, there was also introduced something called full duplex Ethernet, which was exploiting the fact that communications could take place on the cable in both directions without colliding with each other at the same time. And so now the switch could operate without the use of CSMA-CD completely once the switches were introduced and all of the links were full duplex. So this led to the very first Ethernet switches being developed in the early 1990s. And nearly all Ethernet networks today are based on Ethernet switches. It's very unusual to see an Ethernet hub these days. In fact, for 1 gigabit per second and 10 gigabits per second Ethernet, there's no choice. All those networks are switched. So the advantages are multiple concurrent communications, full duplex links, they can send and receive at the same time. And also there's a management benefit that if there are dead or faulty end hosts, they could be isolated by the switch. You could just switch off the link and then isolate it from the network completely to prevent it from harming any other switches in the network. So Ethernet switches have become the main way that Ethernet is put into deployment today. It's just a picture of an Ethernet switch at Stanford. This is the Ethernet switch over here with all these cables coming out, going into patch panels here that go off to different offices in the building. So the way that an Ethernet switch works, it does sort of very simple operations. First is that it does forwarding and learning. We've seen this before. It forwards packets based on its forwarding table, and then it learns the contents of that forwarding table based on addresses that it's seen. So when a frame arrives, first of all, it examines the header of each arriving frame to check for the destination address. If the Ethernet destination address is in its forwarding table, it will forward the frame to the correct outgoing port, or if it's multicast, the set of ports. If the Ethernet destination address is not in its table, it will broadcast the frame to all ports of the switch, except the one through which the frame arrived. And then entries in the table are learned by examining the Ethernet source address of arriving packets. So it'll take the source address, look it up in the table. If it finds that it's not there, it'll populate the table with that entry that says, okay, if ever I see this as a destination address, I now know how I reach it by sending it back out of the port that this address is connected to. So that way, next time the frame won't be broadcast, it'll just be sent on to its correct destination. So that's the forwarding and learning function of an Ethernet switch. And then there's also the sort of topology maintenance. It runs the spanning tree protocol, where it exchanges those things called bridge protocol data units, the BPDUs that we saw in the spanning tree video. And it runs the spanning tree protocol to talk to the other switches to create a loop-free topology. So that allows it to decide which ports to enable or block to make sure that it creates a loop-free spanning tree amongst all of the switches in the network. As a consequence, Ethernet switches are very, very widely deployed. And here's an example of how that might look in, say, a university campus. This is pretty much how our college network looks at Stanford. Inside each building, so this might be a building or one floor of a building. This could be the third floor of my building and the Gates building at Stanford. This could be the second floor. There's another switch for that floor. And then they connect into the building router. They would often be connected in to another router in another building for fault tolerance in case the building router was to fail. And this router might be running OSPF for routing packets around on across our campus. So these routers form the campus backbone that's spread all across our college campus. And then they would eventually connect to a BGP router that connects to the public internet. So this is speaking the BGP protocol to the outside world to exchange prefixes for paths to the outside world. So Ethernet switches can connect many, many hosts, sometimes hundreds of hosts together. There are switches available with hundreds of ports that then connect perhaps all of the end hosts in a building or in the floor of a building. So in summary, medium access control protocols come in two main flavors: random access and deterministic. Random access protocols proved very popular because they're nice and simple. They give transmitting hosts a nice quick low delay access to the network when it's being lightly used. And over the years, CSMA-CD became the most popular. It's a simple access protocol that was used in the first 10 megabit per second version of Ethernet. Over the years, Ethernet standards emerged for 100 megabits per second Ethernet, that's called fast Ethernet, and then gigabit per second Ethernet, and more recently, 10 gigabits per second. Limits on the link size and the need for more capacity meant that CSMA-CD was gradually replaced by Ethernet switching, in which end hosts typically connect over a full duplex link, and so can both send and receive at the same time. And Ethernet switches do pretty much full routing like a router does, but on the Ethernet addresses. They learn the Ethernet addresses to populate their tables by learning the source address of packets that go by. And that way they build up a nice simple forwarding table, and then they use the spanning tree protocol to build a loop-free topology connecting all the switches within the network. So as a consequence, Ethernet switches are ubiquitous today and used in pretty much every organization that has a wired network.